Time to summarize our principles concerning the conservation of linear momentum and energy. So here we will, 1, summarize the basic force momentum and force energy connections, and then lay out which momentum energy equations you should apply to a scenario involving the following. So 2, a scenario involving a single moving object. 3, a scenario involving a system that comprises multiple moving objects. And 4, a scenario involving a system that includes an extended body that is deformable in an inelastic way. So before we begin listing our physics principles, I'll remind you of our calculus principles. Every derivative relationship can be rewritten as an average value relationship by replacing those differentials with deltas. You can also rearrange your derivative into an integral, and the integral is related to the average value by our mean value theorem here, integral over interval. So we can use these to sort of rearrange any of the equations that we're about to list. Okay, 1, force momentum and force energy connections. Impulse imparted to an object by a force from time 1 to time 2 is given by this integral, the cumulative effect of a force acting over time. Compare that to the work done on an object by a force as an object moves along a path with velocity v. So the work done by that force is the integral over that path with a dot product right there. Recall how to handle your dot product, break up that integral into the sum of 3 separate integrals, 1 for each direction, or it just simplifies to this if that force happens to be constant along the path. So the impulse represents the force transferring momentum, work represents the force transferring energy, and that dr right there we can replace with v dt. So the infinitesimal displacement of your object is related to the instantaneous velocity of that object. So making that replacement, we get this, dr becomes v dt, and f dot v reminds us of power. The power delivered to the object by this force acting on the object over this distance along this path, the power is the rate at which that force is doing work, dw dt, which is identical to f dot v here, force dotted with the velocity. Okay. There exists a special class of forces we call conservative forces. They are those that can be written as functions of position, functions of coordinates x, y, and z, or r and theta in polar coordinates. For every conservative force, there exists a corresponding potential energy function u, and the x component of a conservative force that's a function of x, is given by the opposite of the derivative of the corresponding potential energy with respect to x. Likewise, the work done by a conservative force is always path independent and equal to the opposite of the change in potential energy along that path. Okay, so those were our basic relationships. Now moving on to scenarios. We have a lot of equations, so you need to be able to decide which ones to apply to your scenario. So if your scenario involves a single moving object, meaning a point mass or something we can treat as a point mass. And what would that be? What can you treat as an object, meaning a point mass? An actual point particle, if you have something like an electron or some other small fundamental particle that has no volume, that's obviously treatable as a point mass. But we can also treat any extended body as an object if that extended body is rigid, that is, it doesn't compress or change shape, and it is non-rotating. We'll deal with rotating extended bodies later on. But any non-rotating rigid extended body you can treat as an object, a point mass. Okay, so here are the momentum equations that you can apply if you have just a single moving object. There's its definition of its momentum. Here's Newton's second law written in terms of momentum. And here's the impulse momentum theorem for that single moving object. Those are the momentum equations you can apply. Here are the energy equations you can apply. The work energy theorem, which can be rearranged into conservation of mechanical energy. Note here that it is non-conservative forces capable of doing the work that can change the mechanical energy of the system. This is work done by non-conservative forces. And the E here, the mechanical energy, is defined as the kinetic energy of your moving object plus one potential energy term for each conservative interaction that object is experiencing. So these could be gravitational potential energies or elastic potential energies or any other kind of potential energy that is present due to some kind of conservative force, conservative interaction that's present. Okay, 3. What if your system has multiple moving objects? So multiple rigid, non-rotating bodies that we can treat as just point masses. Here are the momentum equations you can apply to a system of multiple moving point masses. The momentum of the system is defined as the sum of the momenta of the individual objects and is equal to the total mass of the system times the velocity of that special point, that imaginary point, that center of mass of the system. Newton's second law combined with Newton's third law gives us this, our conservation of linear momentum equation, indicating that only a net external force can change the momentum of the system, meaning only a net external force can alter the velocity of the center of mass of the system. Here's the impulse momentum theorem for a system, saying much the same thing. An impulse imparted by a net external force changes the momentum of the system. We also have here the concept of pseudo work. This integral here that looks like work but really isn't a work. This is a momentum principle. This says that the net external force on a system integrated along the path taken by the center of mass, so dotted into the displacement of the center of mass, this integral is equal to the change in something we call the kinetic energy of the center of mass. Okay, so this integral makes it look like we've got a force acting right at the center of mass, pushing on the center of mass. But the whole point here is that these forces, this net external force in general, does not act at the center of mass. This is acting at all kinds of other points around the system. That's why this isn't a real work. These forces aren't actually acting at this point. Nevertheless, we can perform this integral, and it turns out to be equal to the change in this quantity. We call this integral the pseudo work. And that quantity is not necessarily the total kinetic energy of the system. It's specifically this, 1/2 the mass of the system, the total mass of the system, times the speed of the center of mass squared. You can also write that in terms of the momentum of the system. The momentum of the system, magnitude squared over twice the mass of the system. Okay, so the whole, not every object in the system is necessarily moving at this speed. So this is sort of like imagining if you took all the mass of the system, put it all at the center of mass, and let it all move like a point mass with this speed. This is the kinetic energy that that imaginary point mass would have. Okay, so it's not necessarily the total kinetic energy of the system, but it's still a useful quantity at times that we can relate to this integral that looks like work but isn't work. And all of this is really about momentum here. This is a momentum principle, not actually an energy principle, although it looks like one. Okay, so that concludes the momentum principles you can apply to your system of multiple objects. Here are now the energy equations to apply to your system of multiple objects. The work energy theorem, much as for a single object. Here the net work is the sum of all the works done on all the objects, and the kinetic energy is the sum of the kinetic energies of each moving object. So conservation of mechanical energy also looks much the same as for a single object. But E here, the total mechanical energy, includes one kinetic energy term for each moving object, like I said here, and then one potential energy term for each conservative interaction. So one kinetic energy for each object, one U for each conservative interaction. Okay, that concludes our energy principles to apply to a system of multiple objects. So lastly, what if you have a system that includes an extended body that is deformable, meaning non-rigid? It can change shape, it can dent, it can bend, it can stretch, it can compress. It is deformable specifically in an inelastic way. That means a non-spring-like way or a plastic way. Plastic being the opposite of elastic. Something that when you change its shape, it doesn't change back on its own. Non-spring-like, that's inelastic. So if you have a body like this in your system, that body will tend to dissipate energy through internal work that is being done between different parts of the body. And that requires a much more sophisticated treatment of thermodynamics than we have at this time. So we can't really use our energy principles to handle an extended body like this. Our energy principles that we have are too primitive to handle such a sophisticated and complex system. So we must stick to momentum principles only, which will include pseudo work. So just to be clear, here are some examples of the kind of system I'm talking about here. An extended body that is deformable in an inelastic way. This would include anything that will dent upon impact, dent permanently and not bounce back to its original shape. Anything with mass that changes shape. So like a real spring, an actual spring that has mass, has some inelasticity to it. And all the springs that we're dealing with at this time, we generally consider ideal springs, which we approximate as massless. So our ideal springs avoid this complication by being massless, but a real spring or any real object that changes shape would be included in this category. And lastly, anything with an internal energy source, an engine or an electric motor or a person or an animal or some kind of explosive, things that have internal chemical potential energy that can be converted into kinetic energy. Any of these are too complex for us to handle with energy. We would need thermodynamics for them. So we must stick to momentum principles only for those objects. So what momentum principles can we use? What are the momentum principles that we can use for an extended, deformable, inelastic body? It's the complete set of momentum principles we were able to apply to a system of multiple moving objects. So all of these, all of those, including pseudo work, up to and including this definition of the kinetic energy of the center of mass, or the center of mass kinetic energy, all of that can be applied to your deformable object. But we cannot apply any of our basic energy, any of these energy equations to our deformable object because its energy transfers are too complex. Okay, one final note here at the end, as I kind of alluded to, an ideal spring, which appears in many of our scenarios. The word ideal there means of negligible mass. We're ignoring its mass. We're treating it as massless. An ideal spring should be considered as not really an object at all. So it doesn't fall into any of our categories here. An ideal spring is really just a construct that represents an elastic interaction. It represents an interaction between two things that do have mass. So we shouldn't think of the spring itself as a real object having mass if we're using this idealization.